let's start on this one, flexible cords and cables. So I've just handed out the practical book, so we'll start on those tomorrow. If you want to have a scan through those, that is a good idea. For this particular unit, flexible cords and cables, if you look at, where are we? We're going to table of contents in here. Oh, here we go. Page 28. Identify flexible cords and cable. So this is something that we'll do in the workshop, but it relates directly what we're talking about today. So if you kind of read that or have that in the back of your mind as we go through it, it might help you. We might start on that one tomorrow. So there's like a couple of boards down in the workshop there that have a bunch of different kinds of cables. So you have to look at them and write down what they are and all that sort of stuff. That's page 28. And as I said, this is a very long slideshow, so we will work through it as best we can. I won't try and finish it today because that would be crazy. So that means the test from this morning's one, isolation and testing. I've already unlocked that one. So that's all you need to do before Monday and finish yesterday's tests if you have not done so. And as I said, because this unit's quite long, we're going to use up our whole time this afternoon doing that one. So we're not going to stay behind and do those tests. But if we had any spare time, that's definitely what we would do. Cool. All right, let's crack into it. Okay, so we start with some definitions from ASNZS 3000. Where are we finding this stuff in that standard? What do those paragraph numbers tell me? Section 1, part 4, which is going to be? No. Good guess. Definitions. And all of those standards, 1.4 is always going to be standards or definitions, generally is. So 1.4.4, active or active conductor. Any conductor that is maintained at a difference of potential from the neutral or earth conductor. In a system that does not include a neutral or earth conductor, all conductors shall be considered active conductors. What does that mean? It's going to go way faster if we just talk rather than just staring at me. So we're back into this kind of legalish sort of language, right? So each of these things require a little bit of thought for us to figure out. What does it mean that a conductor is maintained at a difference of potential from neutral earth conductor? What is another way of saying difference of potential? No, we're on the right track. Difference of potential. What does it mean? What is difference of potential? I really don't know. Starts with V. Voltage. Now, potential difference is another way of saying voltage. So we're saying it's a conductor that is a different voltage from neutral or earth. What's the voltage on neutral or earth? Zero. Good, thank you. Okay, so what that first line is telling us is what then? Difference of potential from the neutral earth conductor. We simplify it. Phase, yes, but if we just reword that sentence to make it more simple, what does it say?
Earth and neutral don't have voltage.
Yeah. So the active conductor is any conductor that's maintained at a difference of potential from the neutral earth conductor. So it's any conductor that what? It has a voltage other than 0. Good. All right. Whew. So an active conductor is any conductor that is a voltage other than 0. In a system that does not include a neutral earth conductor, all conductors shall be considered active conductors. Where would we find a system that doesn't have a neutral or earth? You probably won't know this one. The first one you should have known, but this one, maybe not. Maybe on a 3-phase motor, potentially, I might not need a neutral. I should still have an earth, but then you can get some other odd sort of systems that maybe don't have an earth. We won't normally come across that. Nearly everything we do will have a neutral and or earth conductor. But it is quite common to find 3-phase circuits with no neutral. It will still have an earth, but if you've got a balanced load, then you don't necessarily need a neutral. All right. So there's active. So we talk about phase, we talk about the live conductor, all of those kind of words, but the official word in the standard is active. Aerial conductor, any stranded conductor, including aerial bundled conductors that is supported by insulators or purpose designed fittings above the ground and is directly exposed to the weather. What is that most likely going to be? Overhead power lines, yep. It's an aerial conductor. But it could be any conductor that is in the air exposed to the weather. A cable, single cable core, or 2 or more cable cores laid up together, either with or without fillings, reinforcements, or protective coverings. So a cable is 1 or more cores together. So a cable is something that has more than one conductor. An armored cable is a cable provided with a wrapping of metal, usually tape or wires, primarily for the purpose of mechanical protection. So a steel wire armored cable is the most common example of that. That's where we have our cable and then steel wires around the outside and then another layer of insulation around that. Those are the kind of cables you would bury in the ground directly and maybe in a high traffic area or something like that to prevent mechanical damage to the cable. And also you'd use a steel wire armored cable rather than running something in conduit maybe. If you don't have steel wire or any sort of armored cable, then you run the cable in a conduit to provide your mechanical protection. Cable core is a conductor with its insulation, but not including any mechanical protective covering. So what that means is the cable core is the physical wire itself, the copper, and the insulation around that, but not including the rest of the cable, right? So our cable core are all the wires that are in the cable. And a flexible cable is a cable that conductors insulation and covering which afford flexibility. So any cable that's flexible. That's pretty easy. All right, mineral insulated metal sheath cable, also known as MIMS, is also sometimes referred to as pyro. It's a cable having a compressed, powdered mineral insulation enclosed in a solid drawn metal sheathing. Such cable may be either single core or multi-core. Where have we talked about something that sounds remarkably like that? Yeah, the water element stuff. So this is essentially the same thing. So this is a mineral insulated metal sheath cable, which is usually copper on the outside with that same white magnesium oxide powder in the middle, and then just with copper cores, bare copper cores usually, embedded inside the white powder. They'll be separated inside the white powder, and then the white stuff is packed in there to keep them separate. Any ideas where I might use a cable like that? What does that sound like it would be for? Or a pool? Not so much a pool. It'll have the same limitations as our element in that we can't get water inside it. In fact, it's worse because an element normally comes enclosed in a single thing, whereas when you're doing, what's that? Not inside a heater, but you're right on the right track. So we've got to keep moisture out of the MIMS cable. That makes them really difficult to terminate, because as soon as you cut it, then there's a potential for moisture even in the air to get into that white powder. And you'll also You'll also find that once you start to disturb that powder, if it falls out, then we've got the bare copper wires inside there that are exposed and could potentially short together. So it's really hard to terminate and join and stuff like that. Yeah, you're on the right track. We're talking about a heater. Where might I use MIMS cable? No, because it's going to have a hard outside, so that would be terrible in your blanket. But you both. I think we've got a roll. We definitely had a roll at the old building. I think we've brought it, so we can have a look at that tomorrow. But actually, there's some on that board. But you've identified something there, common to what you're both saying.
What was it then?
70 slides to go. Okay, it's very, very heat resistant. So that same thing as your element, right? That mineral insulation is not going to burn or melt or anything like that. Having the copper exterior protects it. So you'll see that in situations where you're going to get a lot of high temperatures. So in like kiln rooms and stuff like that. It's really uncommon these days. I think I've been to one building where it was in there, it was disused, and the guy I was working with stripped it all out because it's all like copper on the outside and sold it. And that's the only time I've actually seen it used in real life. But it had all been disconnected. But any time that we're going to be exposed to very high temperatures where PVC wouldn't be any good, then we're going to use a MIMS type cable. Neutral screen cable consisting of one or more cores laid up together with or without fillers, surrounded by a concentric wire outer conductor, further protected with an insulating sheath. Geez, they don't make this stuff easy, do they? So when we talk about a neutral screened cable, usually if it's a 2-core neutral screen, or it'd be a single core neutral screen, like if you're running a mains into a house, you have the phase, that just looks like a regular conductor, and you have insulation around that, and then wrapped around the outside is copper wire all around it, and then insulation outside that again. When we use that outer wire is our neutral. So our phase will be in the middle, insulation, and then the neutral will be around the outside, which is a screen around the cable, and then insulation outside of that. So then when you strip it, you grab the outer screen and twist it all together and put a sleeve over it and terminate it like that. Any ideas on why we might use that one? It's a tough question. It's a safety thing. Normally we'd use that for mains cable going into a house or something like that. So from the Toby box at the street into the house, we bury it directly in the ground. And the reason we would use a neutral screen cable rather than just a 2-core mains cable is that if you dig up a neutral screen cable, then there is no possibility of you getting to the phase conductor without first going through the neutral. Why might that be important? Think about if you hit it with a spade. Less likely to get electrocuted? Yes. Why? What if I go all the way through it? Okay, yeah, that's a good point, actually. The neutral screen would act as, like I was talking about with the steel wire armored. But if it was mostly mechanical protection that I was worried about, then I'd use a steel wire armor cable. But it will act like that, so you're probably right. That's not the main reason. What were you going to... Jade, did you say something? No. What will happen is if I penetrate that cable with a digging implement, then I cannot contact the phase conductor without first contacting the neutral, which will mean I'll get a short circuit straight through the blade of my shovel, and it should blow a protective device. There's no way that I can hit the phase conductor only and then get a shock, right? So it's going to short circuit straight across the spade from phase to neutral. The spade is going to act as a short, and then it'll blow the circuit breaker. Right? Make sense? It's pretty neat, actually. I think it's pretty cool. And you might have, so a common neutral screen, you would see just a single core with the neutral screen on the outside, but you could have multi-cores. If we were using a single core neutral screen to go into a house, why does it not have an earth in it? Where in the house? we drive an earth stake at the house, right? We don't need to run an earth wire all the way back to the transformer, because our earth and neutral is connected in our switchboard, and we have our own earth stake at the house. So you won't see an earth wire from the house out to the street. It will only ever be a 2-core cable. Sheath cable is a cable having a core or cores surrounded by a sheath, so it's just that extra layer of insulation, which is like every cable basically. Oh god, one of these ones. I hate the animation ones. Electrical conductors must offer minimum resistance to the flow of electric current. An installation is designed to have relatively small power loss. So the first point there, offer minimum resistance to the flow of electric current. That makes sense, right? That's fairly obvious. I don't want high resistance conductors. When we draw circuit diagrams, we think of our conductors as being 0, right? No resistance. Our resistance is only in our loads. So I definitely don't want resistance in my cables. There will be some, but I want to minimize that where possible. And the wiring of an installation is designed to have relatively small power loss. What do we mean by that in relation to the resistance of our wires? If I have too much resistance in my conductors, what's that going to do in terms of power loss? How? Yeah, we're going to have a volt drop loss. And if we've got a volt drop loss across our cable, then we must have power being consumed, because power equals volts times amps, right? So if I have a volt drop across a cable and a certain amount of current running through it, then I'll multiply whatever that volt drop is times the current running through, and that's how much power is being lost in that cable, right? Does that make sense? So if I've got 10 amps running through a cable from this end of the room to the other end of the room, and I've got a 2 volt drop from one end to the other, then that means 10 times 2. So I've got 20 watts of power just being consumed in the cable. It's not doing anything useful, but I've got to pay for that power, right? So every time I've got that circuit switched on and I'm running that 10 amps, then that 20 watts that I burned in the cable is lost to me. What else might that, maybe not in the case of a 20 watt cable, but what else could be an issue with power consumption in the cable itself? It's going to heat up, yeah, it's going to cause heat, and we don't want heat losses. So we can also see then that the greater the resistance, right, at any given current flow, the greater the resistance, the bigger the volt drop must be, right? And the bigger the volt drop is, then the more power I burn, that power is going to be consumed as heat. So what does that tell us about the relationship between heat produced and current in the cable? Or resistance of the cable, rather. Okay. Yeah. Yes. The more resistance I have in a cable, the more heat is going to be produced, the more power will be burned and heat will be produced, so the hotter it will get. So the higher the resistance of my cable, the hotter it will run at any given, unless it has a negative temperature coefficient. If it had a negative temperature coefficient, then the resistance will start to drop as we heat it up. Yeah, then what would happen? Yeah, so then the more current I put through it, then the lower the resistance will be, and it'll be fine. But normal materials don't have a negative temperature coefficient. Yeah, well, actually, that's a good point. If it has a normal temperature coefficient, then in fact, the more I heat it, then the greater the resistance will be. So not only is it going to get hot because there's too much resistance, then the hotter it is, the greater that resistance is. So then I produce more heat. I don't know, some sort of cycle happens, and then the universe will get sucked into a black hole. So we want to minimize the resistance at all times of our of any cables that we run, and any connections, right? So our connections are by far the most likely point of a high resistance in the circuit. More animations. Conductor. So a conductor belongs only to the wiring. A radiator element or the winding wire in a motor is not a conductor within the scope of the rules. So when we're talking about conductors, all that's saying is it's talking about the wiring in an installation. The internal or the wiring in an appliance is conductors, but then the parts of the appliance that use the electricity are not considered conductors. Jeez, I feel like we skipped something there. For example, a conductor is a PVC insulated conductors in PVC sheathing. What's an example of a PVC insulated conductor in PVC sheathing? What's that? Normal cable, yeah, just any normal cable, any TPS, any flexible cable, all of the cables that are on your desk for the computers and the monitors, that's all just PVC insulated conductors in a PVC sheath. A flat insulated conductor may be used for undercarpet wiring in systems. I'm not really sure why that particular point, although it's true, is brought up there. Yeah, I think that's, no, actually, I think this is talking about a conductor run under carpet, like actual wiring run under carpet rather than yeah. Which, okay, yeah, I guess it's true. I've never seen that done. Yeah, I don't know. It doesn't make much sense to me, to be honest. Yeah, because then I guess your mechanical protection is the carpet, which doesn't sound like a good idea. I don't know. I've never seen that. Let's skip it. So we might have conductors that are uninsulated, right? So we're really familiar with insulated conductors. That's just normal stuff. But we have bare conductors as well, such as buzz bars on switchboards, right? They're still conductors. Yep, it's not an active conductor, but it's a conductor nevertheless. We all know what I'm talking about, eh? Buzz bar on the switchboard, the brass thing where all the earths and neutrals go. Collector wires for trains and cranes and trains. So they're like the overhead lines or overhead buzz bars, like on a crane might have it'll look like a beam that would be made out of copper. That might be your conductor. Bare overhead wiring of outdoor substation too. Like power lines. If we got bare conductors, what's our insulator? Air. Okay, conductors can be bare or insulated, single wire or stranded, and can be various shapes for different purposes. Most conductors used in general wiring are circular and insulated. A cable consists of at least one insulated conductor. Construction of the protected or sheathed portion is mainly determined by the type of service required of the cable. So our conductors are the actual physical copper and the insulation around that, and then we have our sheath around the outside, right? So what this is saying is that our sheath is mainly determined by the type of service required by the cable. So if it's going to be in a very high temperature location, then my sheath might be totally different to something that's a very low temperature situation, like in a freezer. Or if it's going to be exposed to oil or chemicals, or maybe it's going to be exposed to mechanical hazards like stuff hitting it and stuff. So I would use different types of insulation for those different purposes. It's not going to affect the the conductor itself. It's not going to change the resistance or the current carrying capacity or anything like that, but the type of insulation tells us about where we can use that cable or how we would use it. So the types of conductors and cables we've gone through when we did resistivity and stuff way back at the beginning of module 2. We talked about the different materials that are conductors or that conduct electricity. Here we're looking at what are the types of materials that we will commonly use for conductors, right? So mostly copper. So the general wiring that we will have, we will see day to day, and 99% of cases would be copper, right? But we will see aluminium from time to time. I think I've only ever done one installation myself where I ran an aluminium mains. I can't remember off the top of my head why we wanted to do aluminium. I know why I did it. It's because it was spec'd on the plans to run a 35mm aluminium cable, but I can't tell you what the reasoning was, why that was like that on the plan. But it's probably just to do with cost. Aluminium is cheaper. It's not quite as good a conductor, so to get the same capacity of an aluminium conductor, it needs to be slightly bigger than a copper conductor. In special applications, we would use silver, so that'd be like electronics and high performance switch contacts, stuff like that. What's the characteristic of silver that will make it useful? Yeah, it's even more conductive than copper and gold, so it's the most conductive metal. So our copper conductors, advantages of copper. Obviously, it's a great conductor. That's probably the most important advantage of using copper. It's resistant to corrosion in unpolluted environments. Where's a situation where that might not be true? Here's a place that I'm thinking of. Hey, look at the next line. Ammonia and sulfur fumes have a deleterious effect. Rotovagus. Yep, and I've seen air conditioning units where the outdoor units with the fins and the copper pipe are just about falling apart, and not even that old, like 10 or 15 years old in Rotorua, because they get exposed to sulfur, and that sulfur will degrade copper. Our copper cables are easily soldered, so they'll join with solder with a little bit of heat, which is pretty handy. Not all metals will, obviously. It has a high tensile strength. What is tensile strength? Tension, yeah, so stretching. So they have a pretty good strength when pulled or stretched, right? So we can kind of hang them or dangle them, stuff like that. They're not going to stretch and break. So if we're using aluminium, the advantage is lighter than copper. That's one of the reasons that we commonly use aluminium for overhead cables, right? So power lines, you see power lines, they're almost always made of aluminium because it's lighter, so easier to hang them. It's used for solid conductors in large size. It's not often used for small or stranded flexible cables because it's not as flexible as copper. Special techniques are necessary to provide satisfactory joints and terminations. It's quite tricky because has anybody ever worked with aluminium? Not in wiring necessarily, but anywhere, welded aluminium, anything like that? Nothing at all? No. Okay, so played with it. So
Like iron, like that kind of aluminium. Like galvanized iron and stuff.
Yeah, that's not aluminium. Aluminium is aluminium. Usually when you see a piece of aluminium, it's quite dull. It's not a shiny color. Is it? Yeah, no. Okay, well it is. All right. It's quite a dull color. That's because of the oxide layer on the outside of the aluminium. So if you sand it or put a file across it or something, it'll shine up pretty quickly, but then you'll notice that it will dull again pretty fast, and we're talking fast, like within a minute sometimes. So what happens is that exposed aluminium will react with oxygen in the air, and it produces an oxide layer. And that oxide layer, it can be quite helpful because it's really hard and it's really resistant to heat. So if you just get a torch and you melt a piece of aluminium, what you'll see is it starts to melt. The inside will melt first, and then the skin on the outside of the aluminium, the oxide layer, will stay, what's the word, unmelted. It'll stay solid. So you'll see it start to kind of like expand, and then eventually that oxide layer breaks, and then the liquid will run everywhere, which is kind of neat. That makes it really difficult to weld.
We made sinkers out of them.
We could have. Usually use lead for sinkers. Oh, you might have done it with aluminium. Yeah, it makes aluminium really hard to weld because obviously you're trying to join two pieces together, and if they don't melt consistently or easily, then it's not going to work very well. So when you're welding aluminium, you've got to file where you want the joint, and then usually put a chemical on it to stop the oxide forming, and then do your welding. It's highly specialized, and people will generally be specially trained just for welding aluminium. We have the same issue when we're joining those cables, or joining aluminium using it as a conductor, right? So the oxide layer of the conductor is not a particularly good conductor. The aluminium inside is fine, but that oxide layer is no good. So if I'm putting a lug onto an aluminium cable, then where my lug is touching the outside of the cable, that's my join, right? If I've got an oxide layer on that cable, then it's not going to make a very good connection. So I've got to get rid of that oxide layer before I start, and then again put a chemical on it to make sure the oxide layer doesn't reform, not only while I'm doing the joint, but after I've done the joint as well. And that one and only time that I've actually run an aluminium mains, I actually had no idea about any of that stuff. So I think it was only because I went to the wholesaler and I wanted lugs for my aluminium cable. And I think I talked to the dude. There was a dude that I'd known for a long time, so we got along pretty well. And I said, I got to do this aluminium cable. I need some lugs for it. Do I just use ordinary lugs? And he goes, do you have the aluminium joining kit? I was like, what? He said, you need a kit. I was like, where do I get one? He said, oh, well, we have one here. You can borrow it. And then he actually had all the instructions, and he talked me through it. You got to put the chemical on, you sand the thing first, then you put the chemical on, and then they have this special compression tool and a whole bunch of stuff. Which, if that dude hadn't have told me that those joints would have failed almost immediately, I suspect. So I wanted to look like an absolute chump. But as far as I know, that is still working. If you're ever driving to Hamilton and you come down that main road and you'll see the Allied sign on the left-hand side just as you come into town. I built that site, ran all the cables underground, poured the concrete, built the switchboard. I got some photos of it somewhere. Actually, I'll dig up those photos. We should be able to see the aluminium mains in there. Big ass cable. I'll have a look for that. Yeah, so surface oxide that forms on the aluminium has a very high resistance, as it says there. So when we're doing that joint, we can't just join on the outside of the cable without doing anything, because that we're not going to get a good joint. That oxide layer has a high resistance. I'm going to click through the animations. Jesus. No. Aluminium oxide is tougher and harder to remove than copper oxide. And it forms more quickly than a copper oxide, exactly as I said. So that's our main downfall of the aluminium cable, other than it's a slightly higher resistance than copper, is that it's not easy to join. It's not easy to join, not easy to work with, because we've got to make sure that we eliminate that oxide layer. All right, insulating materials. The most common materials used for insulation in cables and flexible cords are plastics, rubber and synthetic rubber, and mineral, like magnesium oxide, that's that white powder. Non-flexible insulation. Yeah, so that mineral insulation is not going to be flexible, right? Every time I bend that cable, if I move the white stuff around inside and move the conductors, then those conductors can short out. It's horrible stuff. So plastic insulation, which is the majority of the insulation that we'll see. We've got two main groups, thermoplastics and thermosetting plastics. The thermoplastic becomes soft when warmed and harden again when cooled. The thermoplastics that are of interest to us are polyvinyl chloride, so PVC, which is your normal TPS flexible cables, and polyethylene. PVC is used to make the common tough plastic sheath, TPS. Now, if we haven't covered that before, that's what TPS means, right? So it's the flat white cable, and we call it TPS. It means tough plastic sheet. Above 115 degrees, the decomposition produces hydrochloric acid, which attacks copper conductors. We don't want to use PVC above 115 degrees, because it could destroy our conductors. Also, cooling it below 0 degrees can make PVC brittle, and it may shatter. So we don't want to use that in super cold places either, because if it shatters, then obviously we're going to expose all our conductors. Operating temperature range of a standard PVC cable and cords is up to 60 degrees, but the composition of PVC can be modified to allow temperatures of up to 85 degrees. Generally, you will see that printed on the cable. So if you have a look at a piece of TPS, it's going to say a few things on there. It'll usually say 2.5 millimeters. It'll say who manufactures it, and it will usually have a temperature rating on there. Maybe not that one, Ollie, maybe one of the black ones. So, I don't know about flexes. Definitely TPSs just generally have it written on them. You can have a look next time we're in the workshop. The modified material is called high temperature PVC. UV PVC is another form of PVC, is treated to provide additional resistance to deterioration from high levels of ultraviolet light. So our normal TPS is not particularly UV stable because it's not designed to be exposed to sunlight, right? A normal flex that you would use for an appliance lead or something should be UV stable because it's going to be out. It might not be outside, but it will be exposed to natural light. Thermosetting plastics undergo a chemical change when they are subjected to heat and pressure and cannot be replasticized by further heat and pressure. The commonest thermosetting material used as cable and cord insulation is cross-linked polyethylene, which is abbreviated to XPLE and often called Xylene. XPLE retains its strength at 90 degrees, so it's a higher temperature than most thermosetting plastics, and has superior insulative property, therefore is particularly useful in high voltage cables. So they're generally pretty flexible. If you overheat them, they'll go hard, is basically what it says. But they will be more resistant to temperature than most PVCs. Rubber insulation. Various rubber compounds are used for cable and cord insulation. The temperature limit required for the insulation determines what rubber compound is used. So up to 60 degrees, we use vulcanized rubber, 85 degrees butyl rubber, 150 degrees silicon rubber. Rubber is not used a lot for cables anymore. You'll see it in houses in like maybe up to the 1930s and 40s. It still exists. There's plenty of houses out there with original cabling in them from that sort of age. The biggest issue with rubber is that over time it becomes brittle. So if you ever come across rubber insulation, the most important thing is don't fuck with it, because it gets brittle and it'll stay there and it'll keep doing its job fine. As soon as you move it, it just crumbles and falls to pieces. And I've done that before. Even something like taking a socket off, and as you pull it out from the wall, all the insulation from around the cores will crumble away, or can crumble away, which means I've got to replace that cable. And I've had situations where maybe I could just re-sleeve it, but then the more you touch it and move it, the more it starts to fall apart, and you just make it worse and worse until you give up. I did my first house that I owned had rubber cable in it, and it was horrible. horrible because, of course, I wanted to rewire everything. That was what I could do. It's like, yeah, I'll put new sockets and do this and do that. And every time you touch something, all the cables fall apart. And I never wanted to. I built a new switchboard in there and did a whole bunch of stuff, but I never wanted to replace any of the wiring. But I ended up probably replacing about half of it just because I wrecked it. Horrible stuff. So we don't use, so that's natural rubber, right? So we're all aware that rubber is a natural product, right? They get it out of trees. Yeah. So and they're legit, like the way that they used to harvest it is you bang a tap into a tree, and then they'll just come along and open the tap and pour the rubber out and collect it up, and there you got your rubber, right? I think the vast majority of natural rubber these days is used for tires. I think tires are still made of natural rubber. And of course, if you want to get into that sort of stuff, have a read up of King Leopold of Belgium in the Congo. Anybody know about that? Nah, that's when the Belgians went into Africa and had heaps of rubber in the Congo, so enslaved like the whole country, and they were like slaughtered and genocided. You know, they just had all these millions of people basically enslaved to harvest the rubber for them in Belgium. Anyway, they had this massive rubber empire across Central Africa, and even to this day, it's not commonly known that like millions of people were killed by those bastards. And there's one dude, King Leopold, who was in charge of the whole thing, and he's just like, I didn't care, kill him. Yes, the history of the rubber trade is terrible. So cable classification. So generally we will have, and you'll see this marked on a cable drum, and then, as I said, it'll be usually printed on the cable itself. There are a number of things that we use, a number of qualities that we use to classify our cables. So it'll be conductor material, our conductor size, so our cross-sectional area, insulation material, number of cable cores, general construction, and voltage grade. So you generally see all that written on there on the little label on your cable drum, right? It'll say CU, for example, would be copper, conductor size 2.5 millimeters squared, and it'll say PVC. It'll usually say PVC/PVC, so that means PVC internal and PVC external insulation. Number of cable cores. Just for TPS, just so you know, it's generally referred to as like a 3-core TPS will be 2-core plus earth. I don't know why, that's just how we call it. So people don't talk about 3-core TPS, they call it 2-core and earth, or 4-core and earth, which I guess identifies something different. Like, you know, we have that strapping cable with the red, white and blue. We would call that 3-core TPS, whereas red, black and green will be 2-core plus earth. So it will say 2C plus E, general construction, I can't remember what that says, and voltage grade, so it'll tell you what the maximum voltage is, which I think for most TPSs, I think is 600 volts. Flexible cables and cords. Flexible cable consists of one or more cores, each formed in a group of wires. The diameter of the wires and the insulated material ensures flexibility. The only difference between a flexible cable and a flexible cord is the conductor size. It's the dumbest thing I've ever heard. So a flexible cord is a flexible cable that is smaller than 4 millimeters. Above that, we call it a flexible cable. Don't ask me why, it doesn't make sense. So the flexibility in those cables comes from making the conductor out of many smaller strands of copper wire, right? So we've all seen that when you're stripping a wire, it's not just one solid conductor in the middle, right? When you get 1 mil cable, that's the smallest that we would normally use, that'll be one conductor. And it's a pain in the ass. As I've shown you all how easy it is to nick a conductor and to break off, right? But if you've got one conductor, then even the smallest nick on that thing and it will eventually break off. So normally if you're terminating 1 mil cable, you'll have to strip it 10 times because every time you do it, you'll nick it and then you've got to redo it. So that makes it flexible, right? Because we think if we had bigger cables, we start talking about 4 mil, 6 mil, 10, 16, 25 mil cables. If they were one solid core, then suddenly they're not a conductor. It's not a cable. It would be like a rod, a copper rod. You wouldn't be able to do anything with it. So having them all stranded, small strands bundled together makes them more flexible. And hence you will also notice then when we're talking about TPS. So for a 1 mil, it's just the one core. For 1.5, I think you usually have 3. 2.5 is 7, I think, and it goes up from there. But when you're looking at flexible cables, they're really thin, right? And we have heaps of them. You've seen that, you know, on a flexible lead. Have we done anything with flexible leads? Well, you've seen what a TPS looks like inside. So a flexible cable, like flex, that you use for an appliance lead or something, they'll be stranded even smaller. So you have heaps and heaps of tiny little strands. So that gives it more flexibility, right? Because TPS needs to have some flexibility. I need to be able to run it around corners and stuff like that. But it's not going to be moved all the time. Once I've installed it, in theory, it'll just sit there forever. Whereas a flex that I use for an appliance lead, that's going to be an extension lead or something like that, you're going to be moving that around, flexing it, throwing it in and out of your van, coiling it up, running it out, heaps. So we need more flexibility in those, hence they have the much, much smaller cores. Number of copper strands is usually 16, 24, or 32. So this is where we're talking about flex appliance leads. Depending on the size of the cord, the conductor together with its insulation is called a core. That's the same as we were talking about before. And here is a lovely picture of such a thing. So here are our conductors made up of lots and lots of tiny little copper strands. We have our basic insulation, so that'll be coloured. What are the colours inside a flexible lead like that? Brown. Who said red? Inside a flexible lead like this, what is our colour? No, blue, brown, no, not black. Blue, brown, and not white. Earth. Green, sort of. Green and yellow. Green and yellow stripe. Yep. So there's our coloured insulation here. We may have some filling materials. That's just to maintain the shape of the cable, right? So we could see there that if I push down on there without a filler material, it's just going to collapse. In most smaller cables, you won't see that. As they get bigger, you'll see it looks like string or rubber or something like that in there. And then this is our outer sheath here. All right, let's take a 5-minute break. So it looks like you're all going to fall asleep. Eh? 5 minutes, where you are. Just have a rest. Because you look like you're all going to die. Yeah, 50 slides. I know.